Hello everyone. Today we are here to present our presentation on compound action potential.
Hi, I am Rudra Ravindra Vengurlekar.
I am Harsh Dhankar.
And I am Rudra Nath Sinha.
Through this presentation, we'll be covering what exactly is compound action potential, how do we measure it, what are its advantages and limitations, and what are its applications in biomedical field. To start us off, Rudra Ravindra will be telling us about what exactly is compound action potential.
Thank you, Harsh. So, before understanding what compound action potential is, let's revise what an action potential is. Here is a schematic of a single neuron. It is dendrite, soma, axon, axon and terminals, and synapse, which will be followed by another dendrite of another neuron. So, when some stimulus is applied to the dendrite of a single neuron, the depending on the magnitude of stimulus, the neuron can undergo something known as action potential. If the stimulus has a magnitude greater than the threshold value, the neuron will get into a phase of depolarization. The voltage difference across the membranes will rise, attain maximum, then it will go repolarization, followed by a refractive period, and it will again come back to a resting state. So this is an all or none type of response. If the stimulus has a magnitude less than the threshold value, it will fail to initiate such a action potential, such a rapid sequence of change in the voltage across the cell membrane of neuron. And only if the stimulus has a magnitude greater than the threshold, this action potential will be generated. So it is a all or none type of response. This action potential is only for a single neuron. But what if we have multiple neurons present in a nerve fiber? Will be able to see a same all or none type of response, or there will be something else? Let's explore. Let's do an experiment. Here is a nerve fiber containing multiple neurons and supporting blood vessels, its myelinated sheets, and connective tissues. So here is a nerve. We are providing a stimulus to this end, and we are measuring the signal here. As we increase the as we increase the magnitude of stimulus provided, we can see response is getting generated, similar to action potential. Why similar? Because up to a point there is no response seen, but after a point we can see this response getting bigger and bigger. It was not the case when we are observing a single neuron, where it is an all or none kind of response. So the peak of this response is increasing and increasing up to a point. It is continuously increasing, not like a zero or maximum. So such a type of response is known as a graded response. But why the behavior of this nerve fiber is very much different from a single neuron, which is constituent of this nerve fiber? So this is because of compound action potential. Let's explore what is the formal definition of compound action potential. It is recording of the action potential of several axons of a nerve when different axons are stimulated together. The different amplitudes and conduction velocities of the fiber account for the compound nature of this response. So basically, all the constituent neurons are not same in the nerve fiber. They have different diameters. Larger the diameter of axon, lower will be the threshold to generate an action potential. And these neurons will get activated first with minimum threshold. Similarly, smaller diameter axon will be the last one to getting activated because they have higher thresholds. So what if we increase the length of this nerve fiber? So here is a response for 80 length nerve fiber for different magnitude of stimulus. So you can see as we increase the magnitude of input stimulus, the response is different. The number of peaks is different, and there are some peaks at later times also, which are not present earlier. So um, we can see an A alpha phase, A alpha peak at 2 millisecond, then A beta phase at 4 millisecond, and so on. So there are one, 2, 3, 4, 5, and 6 different peaks present in this response. So uh, the different diameter not only affect the threshold required to generate action potential, but it also decides the conduction velocity of that particular neuron. Larger fibers have higher conduction velocities and thus contribute to the fast components of compound action potential. On the other hand, smaller fibers have a less conduction velocity and contribute to slow components of compound action potential. So depending on this peak, we can categorize a neuron to different bends. So there are two main ways to categorize neurons depending on these peaks. First one is a letter system. This system is used for cutaneous, means neurons close to the skins. So here are the six types of fiber. As you can see, with decrease in diameter, the conduction velocity is decreasing. So thus we are seeing a delay a larger delay for C peak compared to A alpha peak. These different neurons types have different functions also. The other way to categorize neuron is Roman numeral system. This type of categorization is used for muscular neurons. And here also we can see the same trend with decrease in diameter, conduction velocity decreases. And they have different general functions like muscle middle primary ending, touch, pain, crude touch, pressure, temperature, and etc. So are all the types of neuron equal? The number of different types of neuron equal in the nerve fiber? No. So here is the graph showing the total diameter of fiber and the number. So the nerve fiber having a small diameter are larger in number, even an order of magnitude larger than other type of neuron. And this is true for both cutaneous nerves and muscle nerves. And uh, you can see the variation with size of different neurons. So the the slowest neurons, which are the smallest diameter, are largest in number, which shape the compound action potential. The voltage contribution in the compound action potential is proportional to the square of fiber diameter. So larger fibers will have larger voltage contribution. However, the larger fibers are fewer in number. So that is what we observe in the compound action potential. And depending on the type of neuron present, uh, they have different susceptibility for different blocking agents. So, uh, the B type of neuron are most susceptible for hypoxia. Hypoxia is the condition uh, when the oxygen is less. As oxygen is required in respiration, and there are many pumps on the cell membrane of neuron, which are actively pumping sodium and potassium, and they require energy. So lack of oxygen can negatively affect that. Another blocking agent is pressure. You must be remembering when you keep your hand under your head while sleeping. So when you wake up, you feel the tingling sensation in his hand. But when your head is on your hand, it is under pressure and you don't feel any tingling sensation. So that is the effect of pressure, and it can block the neuronal signals, and it is mostly susceptible for neuron type A. And there are also effect for local anesthetics. It is mostly susceptible for neuron type C. Now Harsh will explain more about why we are measuring the uh, compound action potential, and He will also explore how to measure the compound action potential. Over to you, Harsh. Thank you.
Thank you, Rudra. Now we move on to the question of why do we need to measure or why do we measure compound action potential? As we know, a peripheral nerve is made of hundreds to thousands of axons. Recording from just one axon is very difficult and is not very useful. So instead, we stimulate the nerve and record the combined electrical response of all the axons present, which is then termed as the compound action potential. So, what does it do? Well, it assesses the overall nerve health. CAP tells us about the conductance and the damage or the overall health of the nerve. A delayed CAP indicates that the myelin sheath surrounding the nerve cell has been damaged. It also measures conduction velocity. The CAP waveform reflects fast fibers arriving fast, while slower fibers arriving later. This helps us in diagnosing demyelinating versus axonal neuropathies. And lastly, it also shows population behavior. CAP, or compound action potential, helps us in understanding how many fibers are active and the effects of the drugs or compression on the nerves. Now we come on to the question of what is the experimental setup or how do we exactly measure CAP? So, step 1, a peripheral nerve, for example, a sciatic nerve, is isolated and kept in Ringer's solution. The next step, step 2, stimulating electrodes deliver brief electrical pulses to initiate action potential within the nerves. Step 3, recording electrodes, which are placed at a distance from each other, detect the summed extracellular response, where one electrode is an active electrode and the other is a reference electrode. Step 4, a ground electrode reduces electrical noise and stimulus artifacts. The next step, step 5, the signal is passed through a differential amplifier where the signal is amplified from a low range to a higher range. Step 6, the CAP waveform is displayed on an oscilloscope or a computer screen. And the last step, where the calculation of the conduction velocity is done via the distance, measuring the distance between electrodes and the latency. Here you can see a rough diagram of the step-by-step approach to measure CAP. You can see various components like we have a stimulator here, a data recorder, and a computer display where ultimately the nerve which is displayed here on the bottom is being stimulated by the stimulator. So what is being done here? A stimulator is delivering an electrical pulse across the nerve. Stimulating electrodes excite the nerve fibers. The ground electrode stabilizes the signal, as mentioned previously. Action potentials propagate along the nerve. Recording electrodes detect the summed response. The data recorder amplifies and processes the signal as you can see on the computer display. Finally, the CAP waveform will be displayed on this particular screen. Now, what is the extracellular recording principle that was mentioned in the previous slide? In extracellular recording, electrodes are placed outside the nerve or neuron, not inside the axon. These voltage changes are caused by ionic currents flowing across the nerve membrane. So basically, when an action potential travels along a nerve fiber, Na plus and ions enter the axon during depolarization, where the extracellular region near that site becomes negatively charged, and the potassium ions leave the axon during repolarization. Extracellular region becomes relatively positively charged. These moving charges of sodium and potassium ions create local extracellular potential differences that electrodes which we are using here can detect. Coming on to the detection of signals part, the amplifier, as was mentioned in the previous steps, records the signal between the two electrodes as the V recorded is the potential difference between the active electrode and the reference electrode. Now, this extracellular recording of compound action potential happens in a nerve containing many axons. Each axon generates its own extracellular signal, and the recorded signal is the algebraic sum of all individual action potentials. What is the advantages of this process? This is non-destructive to nerves because it happens outside the neurons. This is suitable for whole nerve recordings and is vehemently used in nerve conduction studies in laboratories. What is effect of stimulus strength on CAP when stimulus is provided by an external source? So, subthreshold stimulus. When the stimulus strength is too weak to reach threshold, no action potential generated in this case and no compound action potential is recorded. Threshold stimulus, a minimum amount of stimulus that excites the most excitable fibers. A small CAP is recorded in this case. Then we come on to the supra-threshold stimulus. Increasing stimulus strength recruits more nerve fibers. The CAP amplitude gradually decreases due to spatial recruitment of axons with higher thresholds. Then we come to the maximal stimulus. All excitable fibers in the nerve are activated. CAP reaches maximum amplitude. A further increase in stimulus strength will not increase the CAP size after this point. Lastly, we have a supramaximal stimulus. This is stimulus which is above the maximal level as was previously mentioned. This ensures complete fiber recruitment. Every fiber has an active participation. The CAP amplitude remains unchanged. That's all from my side. Rudra will take over.
Thank you, Harsh. Hello, everyone. Myself, Rudra Nath. Now that we have seen how compound action potentials are recorded and interpreted, I will discuss the parameters measured, the factors affecting compound action potential, their significance in clinical and research field, and the advantages and limitations related to compound action potential. Firstly, the parameters measured. There are four main parameters measured, which are amplitude, latency, conduction velocity, and duration. First parameter is amplitude, which reflects the number of fibers recruited. A larger amplitude shows more fibers are activated. Second parameter is latency. Latency is basically the time between stimulus and response. Latency is used to calculate the conduction velocity. Third parameter is conduction velocity itself, which is basically helping us to differentiate the different fiber types. Conduction velocity depends on action diameter and myelination. The fourth parameter is duration. In many mathematical contexts, it is also known as the area under the curve. Duration indicates fiber synchronization, that is, spread of velocities among fiber types. Area under the curve is sometimes used as a proxy for total neural activity. Having said that, now we move on to the factors affecting compound action potential. There might be many factors affecting compound action potential. The two major factors are physiological factors and experimental or technical factors. Firstly, I will be discussing about physiological factors. There are two main physiological factors, namely temperature and fiber properties. Firstly, about temperature. We observe that cooling slows down the conduction velocity, whereas heating speeds up the conduction velocity but also blocks at extremities. Second physiological factor is the fiber properties. In fiber properties, I will be discussing about fiber diameter and myelination. In case of fiber diameter, we observe that larger fiber diameters conduct faster and appear earlier in compound action potential. In case of myelination, it is observed that myelinated fibers contribute early to compound action potential peak, whereas in unmyelinated fibers, we observe a lag. Now, moving on to the experimental or technical factors. In this, I will be discussing about two major factors, namely stimulus intensity and the placement of electrode. Firstly, the stimulus intensity. Higher stimulus strength recruits more fibers, thus increasing the amplitude. Secondly, the electrode placement. Electrode placement affects the waveform shape, that is indirectly affecting the amplitude and latency, and which is also affecting the conduction velocity. Now, I move on to the application of compound action potential. The two major applications which has been discussed here are clinical application and research application. Starting with clinical application, there are four major areas of application of compound action potential, namely nerve conduction studies, compound muscle action potential, electrically evoked compound action potential, and spinal cord stimulation. Compound action potentials are widely used in nerve conduction studies, which are routine diagnostic tools in neurology. They help us diagnose peripheral neuropathies, diabetic neuropathy, and other syndrome. In motor nerve studies, the compound action potential or CMAP is used to differentiate between axon losses and demyelination. Electrically evoked compound action potentials are used in studying and measuring auditory nerve response, assess neural health, and program stimulation levels. Compound action potentials are also used in spinal cord stimulation, where evoked CAPs provide feedback in closed loop pain management systems. This help in optimizing therapy and reduce side effect. Now, moving on to research application. In research, compound action potentials are used to study nerve physiology, including fiber recruitment patterns and conduction in multivascular nerves. They play a key role in drug testing and screening, where compound action potentials are considered the gold standard for testing local anesthetic agents. Change in conduction velocity are used to study the effect of ion channel blockers and neurotoxins. Compound action potentials are also important in pain and neuromodulation research, especially in developing closed loop spinal cord stimulation using retrograde electrical compound action potentials. Additionally, computational modeling and simulation of compound action potentials also helps us predict nerve responses in complex systems. Moving on to the advantages and limitations of compound action potential. Now, I will be highlighting the advantages of compound action potential. Compound action potential recording is not invasive or minimally invasive and assesses the whole nerve function. It reveals fiber diversity and recruitment, unlike single unit recordings. Compound action potentials are useful in diagnostic, intraoperative monitoring, as well as medical device programming. Compound action potentials are relatively quick as well as reproducible, and they also reflect the population behavior of the whole nerve fiber. After the highlighting the advantages, moving on to the limitations of compound action potential. Because compound action potentials represent a summation of signals, fiber single fiber details are lost. Compound action potential recordings are sensitive to technical factors such as electrode placement as well as temperature. Compound action potential may be less sensitive in early or mild disease cases and in certain muscle disorders also. Interpretation of compound action potential can be complex due to signal dispersion as well as overlapping fibers contribution. With this, we come to the end of this presentation. Moving on to the summary of our whole presentation. An action potential represents the electrical signal of a single neuron, whereas a compound action potential is the combined electrical response of many nerve fibers within a nerve. Compound action potentials arise because nerve containing different type of fibers that vary in diameter, degree of melanation, and conduction velocity, resulting in a characteristic compound action potential waveform. Compound action potentials are recorded using extracellular recording techniques, and their waveform characteristics depends on stimulus strength and the extent of fiber recruitment. Important parameters such as amplitude, latency, and conduction velocity provide quantitative information about the overall nerve function. Due to these measurable features, compound action potentials have wide clinical and research applications, especially in diagnosing neuropaths, demyelinating disorders, and nerve injuries. Moving on, these are the references which we had used. And yes, this is all from our side. Thank you for being such a great audience and a great listener. Here we end our presentation.